All right, problem 19.2 is using a molecular scene to examine buffers. And one of the reasons I kind of like molecular scenes too is it makes sure that we understand things conceptually, and usually the math is fairly limited because we're not really involving real concentrations. We have to count molecules to see things. So what we have here is 4 different solutions that contain HA, our weak acid, and A minus. So HA is blue and green, and so this little blue here represents the proton that's attached onto the A minus, which is essentially the rest of the acid molecule. So again, when we dissociate that, we're going to have, and they don't show the H plus going off to be with water. They don't show the H3O plus, so they simplify that. So they say other ions in water are not shown. But when HA dissociates, HA is going to dissociate to H3O plus and A minus in the presence of water. But they tell us that these 2 molecules are not shown. Okay, so we've got 4 different solutions here, and we're going to ask some questions. Which buffer has the highest pH? Which has the greatest capacity? And then thinking about converting one sample into another, what would we have to add, acid or base? So let's take this first question here. Which buffer has the highest pH? All right, so considering we have a buffer, it might make sense for us to think about using the Henderson-Hasselbalch equation. And I know we said we wouldn't be using equations here, but we're going to kind of look at this conceptually and see if this makes sense. All right, so using the Henderson-Hasselbalch equation, pH equals pKa plus the log of the ratio of the conjugate base to the weak acid. Since this is the same system here, we're going to have the pKa be the same because that's a property of the molecule. That's the property of the HA. So that's going to be the same between all of these. So it's not even anything we need to consider mathematically. What is going to change, though, is the ratio of the conjugate base to the weak acid. And remember, we talked about in sample problem 19.1, we've got kind of 3 options that we can have here. So if this conjugate base to weak acid ratio equals 1, that means mathematically that becomes 0. If the ratio is greater than 1, that's going to be a positive value, and that's going to increase pH. If that ratio is less than 1, that's going to be a negative value. That will decrease pH. So this problem asks which buffer has the highest pH. So what we can do is we can compare the ratios of conjugate base to weak acid, and we can say whoever has the greatest ratio is going to have the highest pH. So again, we're going to be looking for the largest conjugate base to weak acid ratio for the highest pH. All right, so let's go ahead and look at our different molecular scenes here. Okay, and let's write down the concentration of conjugate base. Remember, when we're writing concentrations with molecular scenes, we're really just counting molecules. So we're going to look at the concentration of conjugate base to weak acid, and then we'll get a ratio. All right, so for molecular scene 1, we can see that there's 3 of the weak acids, 3 of the conjugate bases. So that ratio is 1. Second molecular scene, we've got 4 of the weak acids, only 2 of the conjugate bases, so that ratio is 0.5. Third one, 1, 2, 3, 4, 1, 2, 3, 4. 4 to 4, so that ratio is 1. Buffers 1 and 3 would actually have the same pH, even though they have a different number of molecules. And this is going to become important to help us answer another one of the questions. 4 has 4 molecules of the conjugate base, right? Those are our green spheres, and only 2 molecules of the weak acid. So in this case, the ratio is 2. Since we're looking for the largest conjugate base to weak acid ratio, this guy is going to have the highest pH. Okay, so hopefully that was pretty straightforward and makes sense. Next problem says, which buffer has the greatest capacity? So when we're talking about buffer capacity, again, capacity is the ability to handle anything that is going to get thrown at it. So the greatest buffer capacity is going to have the most numbers of molecules. Okay, so it's going to have the most number of molecules in it. So in that case, we can see, again, greatest buffer capacity is going to be molecular scene 3. So not too much to really think about that. So again, most number of molecules, so capacity is greatest when the concentration of conjugate base plus the concentration of the weak acid is the largest. And so again, if we kind of look at what we have here for scene 1, 2, 3, and 4, and I just add these numbers together rather than looking for a ratio, we've got 6, 6, 8, and 6. So scene number 3 is going to have the best chance at having a great capacity. Question C, should we add a small amount of concentrated strong acid or strong base to convert sample 1 to sample 2? And again, what we can look here, if we look at sample 1, so sample 1 has an equal ratio of conjugate base to weak acid. If we want to convert sample 1 into sample 2 has a depletion of its conjugate base army and an addition to its weak acid army. So if we think about the only way that could happen, we must have added some strong acid. So addition of strong acid means we're going to convert that conjugate base. So again, if we look at it this way, we either have one of these two options. If we add strong acid will react with the conjugate base, and that's going to make HA. So that's option 1. Option 2 is if we add strong base, that's going to react with the weak acid and generate more of this guy. So again, the question is which one of these do we want to increase? Do we want to increase HA or A minus? And again, if we look at this here, HA again being our weak acid, A minus being our conjugate base, to convert 1 into 2, we need to decrease our weak acid. We want to decrease our conjugate base, increase our weak acid. So we want to increase our weak acid. Increasing weak acid is this guy. So we want to add strong acid. So a qualitative problem getting us thinking about what really happens with buffers.